He's a professor and his expertise is in the field of power electronics. When you want, you can start your presentation.
Well, first of all, thank you for the introduction and the opportunity of presenting this work here. Second, I come from University of Oviedo, but also yearlong and Orona are involved in this project. And third, maybe this title is not the most suitable one. Maybe a best title would be this one: how can frequency reduce the cost and size of my battery equalizer? And the answer is the thing that I'm going to try to explain along this presentation, but the answer can also be, well, synthesized in this sentence using it as a control variable, because if I use the frequency as a control variable, I'm going to be able to reduce the number of control switches, which is the main disadvantage of not all, but many battery equalizers. For explaining this answer to this question, I'm going to follow this outline. First, I will talk a little bit about the problems that I have with battery cells and batteries. Then I will explain the solution that we are proposing, the experimental results, just for, well, as a proof of the concept that we are proposing here, and finally the conclusions. Okay, let's have a look at the problem. This is a battery cell, very typical, with a nominal voltage of 3.6 in this case, and it's quite low for many applications. So what we do is connecting several of these cells in series. Okay, we increase the voltage, but if we want to charge them, we have to inject a current, but it's the same current for all the cells. Where's the problem? The problem is that the capacity, the equivalent capacity of these cells is not equal. Manufacturing, temperature, aging, and we have the same current with different capacity. Here we represent the amount of energy we have in each cell. They are discharged. They have a voltage of 3.3 volts, and we want to charge them till they reach 3.6 volts. We inject the current, and as they have different capacity, one of them is going to reach 3.6 volts, the first one. In this case, the third cell that we are representing in the slide. And when this cell reaches 3.6, we have to stop charging this cell, but they share the current. So we have to stop charging all the cells. So we are wasting these red areas over there. We are not taking advantage of all the capacity that we have in all cells. For solving this problem, there are several approaches. Very fast, the equalizer can detect, select, connect to the most charged cell, extract energy, and injecting that energy into the most discharged cell. That means selecting the most charged and also connecting, selecting the most discharged cell at different stages. Another option is extracting energy from the whole pack, okay, and injecting that energy into the most discharged cell, the cell with the lowest amount of energy. And the other way around, another option is selecting, detecting the most charged cell and injecting the energy into the pack. If you have noticed, I've been talking about selecting, injecting, detecting, and choosing or connecting, it doesn't matter, means a lot of switches in nearly all topologies of equalizers. Moreover, switches means control signals. Then I'm going to have many control signals in most of the battery equalizers. And many of these control signals are for floating devices, floating MOSFETs. This adds even more complexity. And also in many topologies, I have to store the energy that I'm extracting, and then I'm going to inject. I need an intermediate source for storing this energy, capacitors or inductors, typically. So this is a problem, and the question is, how can I use the frequency to solve this problem? And well, we think that the answer is yes. Using what is called wave trap. It's a concept widely used in telecommunication systems, but we are going to use it here with in a different way, with imagination. Let's say this is a trap, okay, very simple. It's just a capacitor and an inductor in parallel. Two equations, very simple. This is the impedance of one trap, okay, 1, 0, 2 poles. And this is the resonant frequency of that trap. Now let's connect several of these traps in series, and let's choose the resonant frequency of each trap in such a way that they are not equal between two traps. We would have a situation like this one. Okay? None of these traps have the same resonant frequency. So now let's apply a voltage, a sinusoidal voltage, to the string of traps, and let's say that the frequency of this sinusoidal voltage is equal to the resonant frequency of one of the traps. For example, trap I. Okay, we would be over the gray line in the slide, in that picture on the right hand, and well, what we can say about this: the impedance of trap 1 is considerably low. Also, the impedance of trap 2 and the impedance of trap N. At least they are lower than the impedance of trap I, because my frequency is equal to the resonant frequency of that trap. And if we have a look at the voltages in each of the traps, the voltage in trap 1, the voltage in trap 2, and the voltage in trap N are going to be nearly equal to 0. Actually, all the voltage is withstood by the trap I, the one I selected with the frequency of the input voltage. So I can decide with the frequency which trap is going to withstand the voltage that I'm applying to the string. Another question is, can I take advantage? Can I use this concept in battery cells equalizers? And the answer is that yes, I can, yes, we can. I only have to make some small changes in the previous topology, in the previous schematic. Well, first of all, I have to change the inductor. I have to use a transformer because I have the cells connected in series. So I need isolated outputs in each trap. I still have to define the resonant frequency. So my transformers are going to have air gap, okay? Because I have to define, I have to control the value of the magnetizing inductance of these transformers. But I still have that capacitor in parallel with each trap. And I have a diode, a rectifying diode, because I want the traps to always inject energy into the chosen cell, not extract energy from the cell. And obviously, I need something to provide the voltage to the string of traps. In this case, it's going to be a half-bridge converter. How this works? Well, very simple. It's a, as it says in the title, pack-to-cell approach. I'm going to extract energy from the battery pack, that is from all the cells that I have in series, and I'm going to inject that energy that I'm extracting into the chosen cell, the cell with the lowest amount of energy stored in it. First of all, the control stage detects which is the cell with the lowest amount of energy, with the lowest state of charge, with the lowest voltage. It's not the topic of this presentation. And it will define the switching frequency of the MOSFETs of the half-bridge converter according to this. So I'm selecting one of the traps. One of the traps is going to withstand all the voltage applied to the string. In this case, as before, trap I, okay, and cell I. Then, as the half-bridge converter starts to its operation, starts to work, it's going to extract the energy, and only one diode is going to be directly biased, the diode of trap I. The other cells, the other traps, have the diode reverse bias, so they are not going to affect, they are not going to extract energy from the other cells through the trap. So, am I lying? No, I only have two control switches. Theoretically, we will see that this is not perfect, anything is perfect, and we have some limitations. Also, the number of other devices that I have in this topology is similar to the number of devices, of components, that I have in other equalizers. It's true that I can reduce the number of components that I have in an equalizer, but losing some of the advantages, reducing the performance. And here we are talking about leaving all the performance that an equalizer may have and trying to reduce one group of components. In this case, the control switches, the MOSFETs. But there is a difference to the previous slide. Actually, the voltage that I'm applying with the half-bridge converter is not sinusoidal. The voltage I'm applying to the string is going to be a square waveform because I don't have an output filter in the half-bridge converter, or maybe I have. Let's have a look at the experimental results, not only for proving that this works, it may be a valid idea in certain situations, but also for explaining some maybe interesting points, or at least from my point of view, interesting points. This is the first prototype. This is the first proof of concept. We have the input capacitors of the half-bridge. We have two MOSFETs with SMD technology, so they are in the bottom layer. We have the magnetics and the capacitors, really small capacitors. And also, well, the magnetics, I have to say that they can be implemented in a smaller size, okay? We are using E20 cores because we wanted things not to be very tiny, just to connect probes and make all the tests. And well, the diodes are also SMD technology. We are using only 4 traps. We have in the slide the resonant frequency of each of the traps and the values of inductor and capacitor that we need for obtaining that resonant frequency. What we have here is, in orange, the voltage that we are applying to the string. In green, the voltage of the chosen trap, in this case not trap I, but trap 3. And in blue, at the bottom of the figure, I have the control signal of one of the MOSFETs. And it's true, the orange waveform is not sinusoidal, because, as I have said, I don't have an output filter in the half-bridge converter. But actually, each trap is a filter. I have n filters. So in the end, as you can see, the voltage that trap 3 is withstanding is nearly or close to a sinusoidal voltage. So all the mathematical development that we have carried out is valid, okay? And all the assumptions that we have made are also valid. On the right, what we have is a comparison between the voltage of the chosen trap, trap 3, with a different scale, but the green line again, and the voltage of the adjacent traps, of trap 2 and trap 4. And as we can see, the voltage of trap 3 is the highest. So actually, I can control which cell is going to be charged by the equalizer. Now the question is, OK, I can select the cell. I can say, let's charge cell 3 or cell 2 or cell 4 or whatever. But can I control the charging rate? That is the amount of energy that I inject in the cell every switching period. And the answer is yes. Here we have the same figure. Okay. In green, we have the voltage of trap 3. And on the right, we have also the voltage of trap 3. And as we can see, it's a different amplitude. The difference also is in the blue line. The duty cycle of the control signals of the MOSFETs of the half-bridge converter are different. One is D equal to 0.4, and the other one is D 0.1. I have a control variable, which was the frequency, but I still have the duty cycle. So actually, I can control the charging rate, and the control state, the only thing that it has to do is, well, according to the value of the cell, the charging rate I want, the value of the voltage of the string, well, define a duty cycle or a different one. But I can control it. And the result, yes, well, to see it, we have the voltage of cell 4, actually is the voltage of cell also 2 and 1, and the voltage of cell 3, okay? There is an imbalance, but with the equalizer, we have chosen to keep the charging rate constant, and as we can see, in the end, well, we have achieved an equalization. And yes, well, to finish very fast, the conclusions, it works. It's a valid idea. I'm not saying that maybe that prototype should be as it is implemented right now, but as an idea, it's perfectly valid. We obtain a simpler control, just 2 control signals, just 2 MOSFETs, a lower cost, obviously, and also less failures. This is important. Well, it all depends on the application. Do we have problems? Well, of course. For example, depending on the frequency range, valid frequency range, you will be able to, let's say, place more or less traps. It's a disadvantage, but it's not a problem, because you can always place several of these converters in parallel. You increase the number of switches, but the number of switches is going to be still lower than the number of switches you will have with another equalizer, with the same performance, not always. So this is just an idea. It's not the best idea. It's just another option for equalizers. Now is your turn to decide if this suits your application or not. And maybe for us, the best result, the best conclusion is that, well, yearlong is happy with the result, so it can be something really, really wrong, I guess. So, well, thank you very much, and I will take any questions.
Question.
I have to say, I like the idea very much. However, I have 2 questions. The first one, so it is cheaper to make, for example, let's say that we have 10 cells. So it is cheaper to make 10 transformers than to use so many switches like
It's cheaper to have 10 transformers and 2 switches than 10 inductors or 10 transformers and 10 or 20 switches. We are keeping the number of the other components constant. what we are reducing, we are not reducing the number of all the components. We are reducing the number of control switches, and we keep the number of the other elements, capacitors, inductors, transformers, constant, for the same performance. Of course, you can have a look at literature, and you are going to find, for example, based on the flyback topology, a reduced number of control switches, just only one, and just one transformer with several output windings. So, well, in the end, it's going to be a bigger magnetic. The problem is that you don't control which cell is going to be charged perfectly. You depend on the voltage of the cell and on the leakage inductance of that flyback with multiple outputs. So, for example, there, the precision, the charging precision that you have, let's say the minimum amount of voltage that you can inject in a chosen cell is limited. It's a worst, from that point of view, it's a worse topology. But it all depends. If you want something cheaper, none of these. Nothing based on transformers or converters or whatever. Just a MOSFET and a resistor. It's the cheapest way.
And the second question is, when you made the traps, I saw that actually you had totally different combinations of L and C's.
Yeah.
So I mean, wouldn't it be easier to try to maintain the same inductance and tune the same?
Yeah, tune the capacitor.
Because I mean, if you want to have it, I mean,
yeah, in natural implementation, it's easier to have equal components and different components. Yeah, but you are going to lose performance because then we have to enter in mathematical development, which I didn't want. But you have to take into account the Q factor of the filter. You have to take into account that depending on the combination, you are going to have different resonant current in each trap. What we want to do is reduce that resonant current that we are going to have in the inductor. So we try to always, maybe I'm saying the other way around, but increasing the value of the L and decreasing the value of the C, just to reduce the resonant current that you are going to have over there.
And for example, are you thinking about some kind of auto-tuning?
Yeah. I mean, I haven't mentioned, but why did I have all the resonant frequencies with a distance of, well, I don't remember, but let's say 100 hertz? Why not 10 hertz or 1 hertz? Because you have to take into account the tolerances of the components. I haven't mentioned because, well, I didn't have time and it was out of the scope here, but you have to define the resonant frequency of each trap just not to overlap with the resonant frequency of another trap, taking into account the influence of tolerances. So there's a lot of things that you have to consider. So
but how do you deal with the tolerances of the
we consider, we start with the first trap, with the first resonant frequency. We say, okay, these components are going to have the capacitor a tolerance of 10% or maybe 5%. The inductor transformer is going to have a tolerance of, let's say, 10%. These calculations are done with 10 and 10%, yeah. And we define which is the range, the real range in which the...
But do you track the optimum point?
I left the question half answer, sorry. Yeah, it's an idea, but we haven't done yet. We are thinking about making a frequency sweep and detecting where are the resonance of each trap. But, well, is the first stage of this project.
I think just one more questions because there are 3 or 4. Okay, we continue.
Pablo Zumel from the University Carlos III. How is the current waveform injected to each cell? Because you have a...
It's a resonant, to make a short answer, it's a resonant current defined by the capacitor of the trap, the leakage inductance of the transformer, and in a second order of influence, the magnetizing inductance of the transformer.
And the cell is happy with this current waveform? I mean,
you can control the peak you are injecting.
But the harmonics injected to the...
Maybe this answer should be given by an expert on batteries. But I guess that, yes, it's true, it's not constant, but, well, you can always, if you want, place an output capacitor if you want to filter something.
Thank you.
Pedro Alou from this center. Very interesting presentation. I have a question about, you have presented how it operates once the system is unbalanced, okay?
Mm-hmm.
And I was wondering if you are planning to use it during the charge process. I mean, imagine that all the batteries are discharged,
Yeah, you have a
and then you start to move or select which cell is.
Yeah.
It's just to avoid the imbalance from the very beginning.
Yeah.
I don't know if it is easy or not, or are you thinking about that? Or?
That we have in simulations,
Mhm.
and there's not much problem
Mhm.
in simulations. I have to say that this is a real test, but maybe for lazy researchers, because rather than using real batteries, battery cells, then this time could be minutes or even hours. We are using capacitors. So well, it's a challenge for the system, because it has to have more reaction, more capacity of reaction. But maybe there's a problem, yeah. But in simulations it works. With batteries in which all the time is longer, maybe you can make it all slower, and you are not going to have problems, I guess. But I have to say that we haven't tested yet in experimental results or in experimentation.
Thank you.
Okay, last question.
Vladimir Šiković from UPM. I wanted to ask, how close can you put resonances of the traps, and how that affects the efficiency, since if you have 10 traps, for instance, you're going to have a really wide range of operation of your converter. And how will that affect on the losses, since I'm assuming that you're optimizing the efficiency as well?
Right now, what we are saying is, if you have a converter, it's going to have a higher efficiency than a MOSFET and a resistor, but we haven't measured the efficiency. It's true, but we guess that the efficiency is not going to be very bad. Which is the difference on how do you deal with the different value of the resonant frequencies? As I've said, are tolerances. So I'm not an expert on an industrial implementation, and that's, let's say, it's on the hand of Ikerlan and Orona. I don't know which is the tolerance that they can get in their components, inductors and capacitors.
Okay.
And yes, I mean, ideally, the voltage in the chosen trap is the input voltage, and the chosen in the other traps the voltages are 0. In the experimental results, it's not as nice as in
No, I was thinking if you, for instance, want to charge 10 batteries, balance them, and you have resonances on a certain band, you're going to operate from 10 kilohertz to 1 megahertz.
Yeah, true.
And how you will have one power stage.
Well, I guess that the power stage should be developed by GAN guys, I guess. Not me. No, but no. That's a good question. There's a trick. I mean, it's true that you have many inductors, you have many transformers, but the current through the inductors, which are not on this electric trap, is 0. So actually, you have to define each inductor, each transformer, for its resonant frequency. It's going to operate at its resonant frequency. So you don't have to, let's say, design a wide frequency range inductor. Another thing are the MOSFETs, and maybe silicon MOSFETs are not the most suitable one.
Okay, thank you very much, Manuel.